We now move to something more specific. We try to start from what you better know, better. That is analog amplifiers that you studied in analog electronics, the basic analog electronic course. In a typical analog circuit, as in operational amplifiers, the amplifier must pay attention to the following aspects. We want to amplify the signal, voltage or current. We want to be linear. The transfer function needs to be V out equal V in multiplied by the gain, or the current must be the input current multiplied by the gain. So it must be linear. It is important the frequency range of the output signal. If too fast or too slow, it will not be amplified properly. And we will also focus on input and output resistance of the circuit. Input resistance, otherwise not all the input signal is transferred to the amplifier. And the same for the output resistance. If these are not matched, not the entire output of the amplifier is transferred to the output resistance, to the load. We never discuss about power gain. It's not the main goal for the power stage. You never discuss, okay, I want 1 milliwatt, the input signal is 1 milliwatt, I want to transfer 2 watts to the output load. It's not something that is important for an analog amplifier. This is an exception for radio frequency power amplifiers that you need to transfer a certain amount of power. But as I said before, radio frequency amplifier is not the focus for this course. This is the case, for example, of a radio system. We have the signal from the antenna, and this is very small. We want to amplify this value in order to transfer the signal to the processing unit, that is to the needs to modulate or demodulate to extract the signal from the data. And here the problem is match the input resistance so that the entire signal is transferred, or most, the maximum signal is transferred to the processing unit. We can also have a problem of too much power. If the power transferred to the processing unit is too much, this will hit and can be destroyed, or there can be an overvoltage. On the other hand, if we want to drive a load that needs a certain amount of power, the design focus is different. Here we focus about the power, and we have a power circuit here with a power supply that needs to transfer this power to the load. There will be an input signal that will modulate this power transfer, the drivers, but in the end, the most important aspect is the efficiency, the ratio between the power transferred to the load and the power drained from the power supply. The efficiency is always lower than 1. You cannot create power, energy, usually expressed as a percentage of 100%. You studied power amplifiers, analog amplifiers, the basic, the class A amplifier, so this is a repetition for you. Something that probably you did not mention during the previous lectures is, for example, the power dissipation on the active device. Why bothering about this aspect? I need the input power the output power, I design the circuit on this and everything works. The reality is that if the power is high, the current will be high, the voltage will be also high, the power device can be destroyed, or because of the voltage, or because of the current, or because of the power dissipation that will heat up the device, and in the end this just will melt. In this case, the power gain between input and output is also relevant. We now focus on power. Classes of operation of power amplifiers and power circuits. Now, this is a typical application for audio systems, for example, and the idea is transferring a sinusoidal signal or the sum of sinusoidal signals. So the focus is the input is a sinusoidal waveforms, and I want to transfer these waveforms to the board. We have class A amplifiers, in which the power device will conduct current for the entire period of the input signal. This is 360 degrees. In class B amplifiers, the power device, usually there will be two power devices, because one of them will conduct for just 180 degrees, just half of the cycle. So this means that usually you have another device that will conduct for the rest of the period. Then we have class C, class D, class A. We focus on class D devices, class D amplifiers, in which the device will conduct for very small periods and actually is switched on and off. And we will see how this can work to produce the output signal. We will briefly discuss class A and class B device amplifiers, just to understand why class D is much better. Class A operation, this is the typical switching made in switcher schematic circuit. It's just an emitter follower configuration. The collector, this is designed with the BJT, just to be close to what you had done before. The device is biased at middle point of the characteristic. When the input is 0, the device will work here. Please note here we have quite large voltage and also quite large current. It means we are dissipating a lot of power. When the input signal will swing from the maximum to the minimum, the power device will move the operating point to almost 0 current maximum voltage to almost minimum voltage maximum current. Will move like this. There is never an instant in which the device will not conduct, and this is a class A amplifier. Further, there is not a single in-time instant in which the device does not dissipate any power, and this is a problem. This is a very simple schematic circuit. We can simulate it later on. The calculation of the maximum power efficiency, assuming a sinusoidal input, is quite easy. These are the formula. However, we need to calculate the power absorbed by the two power supplies. There is this power supply here, the plus 12.5 volts, and there is also this power supply here, minus 12.5 volts with this current. This is a current generator, but in reality there will be MOSFETs or the BJT that make it. But however, this is a constant current. These two power dissipation for the negative voltage power supply is just the collector voltage supply voltage multiplied by the output current. zero current, while for the positive supply voltage is more complex, but however it's quite simple because I multiply the voltage by the integration of the current, that is the collector current, divided by the period. In one period this current will be just I0, because it will be I0 plus one sinusoid. The sinusoid in one period is 0, and this is the result. So these two power supply will just dissipate the same amount of power in one period, and the power dissipation is twice DCC multiplied I0, which is the power provided to the load. The load will have a sinusoidal output with a peak value Vp, and the peak current will be Ip. Just integrate the multiplication of volt and current to get the load power, that will be Vp Ip divided by 2. The maximum power that you can imagine to transfer to the output, you get it when Vp is equal to Vcc and Ip is equal to I0. This is not possible in reality, this is just an ideal value. In the end, you get this is the maximum power that you can transfer to the load, and the maximum efficiency is that 1/4, that is 25%. Very, very, very low. Now, let's focus on the power dissipated on the device. We can write down an equation for the power balance in the circuit and say that the power from the power supply is equal to the power dissipated on the device plus the power dissipated on the load plus the power on the polarization circuit, and this the negative supply circuit. The maximum power dissipation in the circuit is obtained for 0 power on the load, PL equals 0. The polarization power is constant, we calculated it, it's VCC multiplied I0. In the end, the maximum power dissipation on the device will be PS minus VCC I0 is equal to VCC I0, that is 50% of the entire power. Remember that the maximum power efficiency is 25%. Let's put down some number and try to understand what this means. Imagine I want to drive an output load with 50 volts. It's not a huge power. This is probably much higher than 50 volts. In order to obtain this controlled power output of 50 volts, I need the supply voltage able to provide 200 volts. I need to take 200 volts from the plug in order to have an output of 50 volts. A huge waste. In the worst case, 100 volts will be dissipated on the power device. It means that in the worst case, if this is driving 50 volts to the output, in the worst case, 100 volts of power will dissipate here inside the circuit, will heat up the entire system, and this is not easy. If you remember the 100 volts bulb, the lights, when we had incandescent lights, have you ever seen a 100 volt bulb? It's very bright and it's hot. It's incredibly hot, you cannot touch. And this means this is the problem of power efficiency. It's not the waste, it's not only the waste of power that is very, very important. The other problem is the huge heat that you need to dissipate. The system must be big, you need fans, heating system, cooling systems, and so on. These are some suggested exercises. Which is the power dissipation on the device when the maximum power is transferred to the load? In this case, you can calculate that the power is, in this case, is just the power that you transfer to the load. 50 and 50 volts. So also in the best case, you can say, okay, but I will never work with zero power on the output. I will work always driving the maximum power to the output. So it's 50 volts to the output. Okay, but it's also 50 volts on the power device. You are not improving it a lot. You are wasting a lot of power and the heating will be high. Imagine that you want to drive a loudspeaker, a speaker for audio amplification. The typical input impedance, let's say, is in the order of some ohms, let's say 5 ohms. The loudspeaker will be driven with 50 volts, it's not very high audio power. Which are the peak voltage and current that the BJT needs to handle? You can calculate very simply volt and current, and you start saying that the maximum voltage on the device is 30 volts. More than 30. In this case, you need to be safe. So probably you need to buy a device that can handle 50 volts. And the maximum current is 5 amps. These are not simple and small numbers. If you try to build a small circuit with an amplifier, analog amplifier, probably you used a very small transistor and the output current should have been 10, 20 milliamps. These are the numbers that you use in your analog electronics exercises. And the volt will be 5, 10 volts. Here, the voltage is 10, 4, 5 times that much, and the current is 5 amps. It's a big power, big current. Other suggested exercise, calculate the efficiency for a constant output voltage. I can start, okay, but this is an application when I have a sinusoid, in which I have a sinusoidal output. In real application, in many power systems, you need a constant output voltage. So let's see what happens if I use this like an constant output voltage. You can easily see that the power efficiency is not that good. Also in this case, it's very, very low. Class B operation, in this case you have a push-pull configuration, you have two devices, in this case one NPN, one PNP. One will drive the positive current, the other one will drive the negative current to the load. In this case you are biased so that when the input voltage is 0, the output current is 0. In this case, at least, when there is no input, you have no output power and no power dissipation. This is quite good. However, you can calculate the power efficiency also in this case, calculate the power absorbed from the power supply. You need to integrate from in out period the sinusoid, you get some grid P on the denominator and some very simple calculation. You can do this by yourself at home to check if there are errors in these equations, but in the end, the power efficiency, the maximum power efficiency is 78.5%. Please note the maximum here. It means that this is the optimum. If you cannot get above this, the reality will be much lower. It's better, much better than 25%, but not good enough. Also in this case, you can calculate the power dissipation on the device, saying that the power taken from the power supply will be the sum of the power dissipated on the load and the power transferred to the load and the power dissipated on the power device. You, in the end, obtain a quadratic equation as a function of the current. You can calculate the maximum, calculating the derivative of this, of the power dissipated on the device as a function of the current, and the maximum will be obtained from this IP star current. We will substitute IP star in A and get that the maximum power dissipation on the power device is this one. the ratio between the maximum power dissipation of the power device and the maximum power transferred to the load will be 0.40%. Good, better, but not so good. The total power dissipation on both devices is 40%. Each device needs to dissipate 20% of the maximum output power. Again, for a class B power output of 100 watts, we need a power supply that needs to handle 130 watts, and each device needs to dissipate 20 watts. It's much better than class A power conversion power circuits. In terms of performances, we are paying this with some issues for the linearity. When one device starts conducting and the other switch off, the transfer function is not actually linear, and this will create some distortion on the output. For audio amplification application, this can be a problem. But in general, still also in this case, if the output power is very high, you cannot sustain this 20% waste in the worst case on the power devices. For a 10 kilowatt applications, this means that our power device will need to handle and dissipate 2 kilowatts. 2 kilowatts is a heating system that will keep this room warm, very warm, for an entire day. It's impossible to dissipate all this power on a single small power device. Some digression here. I use the term package because the heat needs to be dissipated by the package. If you were not present during my PGI lectures, the package is the plastic, metallic or ceramic box that surrounds that. This should have a double R. That surrounds the piece of silicon, the chip, where the power device, in which the power device is manufactured. This sentence is very badly written. However, the package is needed for mechanical reliability and for protection from environmental humidity, chemicals, dust, and various pollution. These are typical packages for discrete device. This is the TO220. For power devices, you can see this metallic part. For signal devices, you don't have the metallic part usually. It's not so important, but this is important since you have to dissipate the heat, and the metallic part will ease this task. You can, for example, screw some additional metallic part there to help the cooling. This is another discrete device, the package, and this is a surface mount. The size of this one is more or less the size of this, but as you can see, the metallic wing here is smaller, and the pins are bent in order to be soldered on the package, on the PCB. Now we understood that class A and B power series are not that efficient. We need something different. The problem we have seen is that the devices will dissipate a lot of power. They dissipate a lot of power because they stay for a long time in a condition, in an operating point in which you have a lot of current and a lot of voltage. In order to increase the power that you can transfer to the output and improve the efficiency, we need to decrease the power dissipation of the active devices, the circuit. This is to increase the efficiency, and also this allows us to buy less expensive and bulky power devices, because they can be smaller, can be cheaper, the packages can be less stressed. This is why, in the end, the dissipation of power devices is limited by the package, their size. Big devices can dissipate a lot of heat. Small devices will dissipate less power. The best way of reducing the power dissipation of the devices is to let them operate into two limiting operating points. The off state. In the off state, the power dissipation is zero because the device current is zero. Power is current multiplied by voltage. Current is zero. Power is zero. On state, in which we bring the devices in the full conduction. The current will be the maximum here, but the voltage must be very, very low. You have very low on-state voltage drop, let's say almost zero. And also in this case, the power dissipated is small. Let's say that we want to work, better to see here. Here for the off-state, and here for, let's say, here for the on-state. Small voltage drop, even if the current is high, the power dissipation will be small. This is the class D operation. In these devices, in these circuits, the device will operate as a switch. There will be either off, or open, off state, or on. Closed ends in the on state. The device will be driven by input pulses that will switch it on or off, no intermediate states, and they can operate at much less dissipated power, than the output power, and this will increase output power and efficiency. As previously said, in the off state, I do expect that the power dissipation is very small because I have the maximum voltage, okay, but the only current is the leakage current, it's negligible. And on the other hand, in the on state, the maximum current, but the on state voltage drop must be very small, it must be a fraction of VCC. For a 50 volts application, I do expect a 1 volt VCC, the on state voltage drop. This means that the power dissipation will be small. There will be another source of power dissipation, the transient or dynamic power dissipation, because switching from the on state to the off state will mean that the device needs to pass through the operating points where the power dissipation is higher. This must be taken into account and must be calculated. However, if this transition is very fast, if I move from the on state to the off state in very small time, I can dissipate small amount of power. This is why I want to be fast. I want fast devices because the switching power will be hopefully smaller. In class D operation, the power device can easily handle a significant amount of power. The limitation is not on the static power. Usually there is a limitation on the dynamic power, but it is less stringent because the dynamic power that you can handle is much higher than the static power because you switch them on and off. And usually you have a limitation on the maximum current and on the maximum voltage. For example, if you want to design a circuit with 50 volts of output and 2 amps of output current, that is 100 watts, in class A operation I need to choose a power device with ratings of 50 volts, 2 amps, and 50 watt of maximum power dissipation. In class D operation, the power dissipation that can handle can be also as low as 10 volts. Since on-state voltage drop is about 2 volts, and this means that when the voltage is the maximum, when the current is maximum is 2 amps, I will have a 2 by 2, 4 watts of power dissipation. I need to add to this value the dynamic power dissipation here and there. In the end, let's say we can say that 10 volts will be enough for this application. This is another viewpoint from the same operating principle. This is for a BJT device. The operating load line will switch as fast as possible from this point where the power dissipation is very low to this point where the power dissipation is also very low. And this will save power and will increase the efficiency. This is an example of what happens when you switch from the on state to the off state. We can define an average steady state power dissipation, let's say PDS, PD static, and an average dynamic power dissipation, PD dynamic. The power dissipation in the on state is happens here and here. Here the device is on, the current is at its maximum, and the voltage is not zero, but it is very low. You need to simply multiply this value by this value and you get this power dissipation. The power dissipation will be the minimum voltage drop, the on-state voltage drop, I will call it later, multiplied by the on-state current, and this also must be multiplied by the period of time that the device is on in an entire period. That is the on time divided by the period. If the on time is very small, this will further reduce the static power dissipation. During the off state, on the other hand, you don't have static power dissipation because the leakage current must be very low. Hence, voltage multiplied by current is negligible. But as you can see, there will be the transitions. Here, while the current is decreasing, the voltage is increasing. If you multiply current by voltage, you have a peak here. Now, the shape of these two curves are not linked to the real behavior of the devices. It's just to show what could happen. The behavior depends on the device, depends on the driving circuit, depends on the load. There are many things that can change the shape of these cars. However, let's say there will be a peak of power dissipation here and another peak of power dissipation here when you switch the device on. The current increases before that the voltage is gone to zero, and this will provide you an increase of power dissipation. The dynamic power dissipation can be calculated like the integral of the current multiplied by the voltage during the switching periods, divided by the period of the switching period. The total power dissipation of the device will be the sum of these two components. Now, in a class D amplifier, the input signal, the information content of the input signal, cannot modify the amplitude of the pulses, because the output device can only bring the output, let's say, from 0 voltage to minimum voltage to the maximum current. Maximum current, minimum voltage to maximum voltage, minimum current. So you have a pulse. You cannot control the amplitude of the pulse. The only way to transfer the information from the input to the output is to control to modulate the width of the pulses. Not the amplitude, but the duration. In this way, you obtain a pulse width modulation of the output.
And this information needs to be transferred to the load to obtain the output signal. The simplest way to obtain a pulse width modulation is using a signal comparator. This is the input signal. This is a sawtooth signal. Each time one is smaller or larger than the other one, the comparator will switch on and off the output devices, and you get these pulses that whose width is proportional to the input signal, more or less. This is one example. This is the input signal, a sinusoidal one, in blue. The sinusoidal signal, the input signal, has a frequency that we call Fs, frequency of the signal. The triangular waveform that's used to compare with is in green. This is with a frequency that is Fm, the frequency of the modulating waveform. Every time the green curve is higher than the blue curve, the output goes to 0. On the other end, the output goes to the maximum. As you can see, when the blue line is as a high value, these pulses are very wide. On the other end, when the blue line is very small, these pulses are quite small. So the information of the amplitude of the input signal is transferred to the width of these pulses. If you filter this red waveform with a low pass filter, you will get the sinusoidal input again. This will work. However, we will discuss this later. This only works if the modulating frequency is quite much higher than the signal frequency. You want to switch. You want to have many pulses that will construct again your input signal. This is a very simple example of a Class D amplifier. This is the input signal, a sinusoidal one. This is the generator of the triangular waveform. This is the comparator. It's not a very simple comparator because there are some tricks in this circuit that are not obvious at the first glance. And these are two N MOSFETs that will drive the output to the maximum or to the minimum. Will be on and off each of them. This is very similar to a CMOS inverter. The trick there for the negligible static power dissipation was that when this is on and this other is off, and this is the same, you never want to have them, both of them on. If the both of them on, you have a short circuit current, and this is waste current, this is wasted power. You want to switch this on when this is off, and vice versa. You get here a pulse with modulated signal, and this is a low pass filter, an LC low pass filter that will reconstruct the sinusoidal input to the output.
This is the previous circuit, the class A amplifier. Exactly the same. What we do expect here? The power needed for this negative supply is 12.5 volts multiplied by 0.5 amps, 6.25 watts. The same from the other power source. So in the end we expect to sink 12.5 watts from the power supplies. We do expect in the maximum power efficiency 1/4 of this power to the load. That is 3 point something watts to the output. There is something wrong here. No, this is the wrong circuit. This is the same circuit with the sinusoidal input. This should be the simulation. We can see here the input voltage in green and the output voltage in blue, light blue. They are not exactly the same, and here we calculated the power dissipation taken from the load, from the power supply, and this is the power transfer to the load. You can directly see that this is much higher than this. You can integrate. In this case, we are lucky. There are just a finite number of periods, so just the integration in this area will give us a reasonable value for the output. Here I have to no. I don't remember, or better, I can do this with the mouse. I don't know how to do it, how to integrate. The integration is control left. I do this automatically. I don't know how to do, I don't remember how. The power dissipation from the power supply is, as you can see, 12 something watts. This is what we expected. On the other hand, the power transfer to the load is is 2.26 watts. We expected 3 something, and we go much worse. It's much lower than 25%. This is probably 15% efficiency. You can't go much better than this. Perfect. This is what we expected. We can also, on the other hand, see what happens for a class D amplifier. This is the same class D amplifier, the one I showed during the lecture. This is the simulation. Okay. First of all, the input voltage is a sinusoidal one. The voltage on the D node, that is the output here. The D node is the output of the power devices here. So we want to see a number of pulses. These are the number of pulses. As you can see, there are pulses that are wide here and 0 here. This sinusoid here, V out, is the output of the low pass filter. As you can see, you can easily transfer the signal from here to there. We can calculate the power efficiency. In red, we have the output power. And in light blue and cyan, the power dissipation for the two power supply. The number here is 5.3 watts. The number, I don't know if it's better to, let's see if the 5.3, okay, it's the same. And here I have 2.9 and here I have, no, not shift, control, 2.6. The total is 5 watts. No, 5.5. And this is 5.3. The efficiency is good. Let's say more than 90%, around 90% maybe. It's not that exceptional, however. It's not the maximum. The problem here is you can see a number of pulses for the current. Here you have this peak. These are exactly the period in which, notwithstanding my effort to avoid them, the devices still conduct a bit together. And you have this short circuit. If you fail a bit with the sign, the efficiency drops dramatically. And as a matter of fact, this is a driving circuit that tries to avoid contemporaneous conduction of the two devices. In the end, however, Class D power amplifiers can provide much higher efficiency than Class A and Class B. And this is not a very sophisticated design, it's just something that I made for teaching purposes.